There's no reason to do that. You get paid education.
You get paid and then
You get paid like any other.
Every interaction I have, people should pay me. That's not a blessing.
Well, like it's setting.
Well, you're also, they're also blessing.
Yeah, so you did.
Now, go there.
Yeah, now you can fucking voice those.
Paid, so like then like.
Just like the.
Yeah, it's people I get paid for talking.
Yeah.
Why are you looking at that?
That's.
You have the whole point. They never
I mean, but the arts-
say that ever, you know,
Okay, I didn't get a chance to quite finish, 6.5 with even malfunctions, so, I'm gonna try to cover both these topics, but I also want to just go ahead and have me check the homework for both of these on Monday, because I know some of the problems we didn't quite get to.
Okay. Perfect. Good. I mean, like, it's like an
Yeah.
Oh, that's true. I left all my stuff at home, so I was wondering if I need to pack it up there.
Yeah. Let's just follow along. Shouldn't expect me. Hey, guys, page 46.
Live it for 10 years. I had so much love and I got paid for it. It's not really so. That's what happened. I was like, I'm not getting it. I can't do it worse. That's like one of them's going in and script. I get paid. I have to do school. I have to do school. I get paid. I love it.
Even in 2020.
I should do friends.
Some years ago.
Okay, so, page 46. Before I get into even odd functions, let me just highlight that we can treat integrals as regions and area related regions. So it says, suppose the depth integral from 3 to 10 is equal to 9. The integral from -1 to 3 is equal to 5. Find the depth integral from find the area or the region from -1 to 10. Why don't we create something that is more straightforward, because we know that the depth integral from -1 to 10 can be broken up based off of the boundaries that's presented here as the sum of what two integrals? Well, -1 to 3. And then plus the integral from 3 to 10. And the reason why we want to pick these bounds is because these are related to what's given to us, right? So we have one region from -1 to 3, another region from 3 to 10. We know if we add these up, we're going to get the full region from -1 to 10. Yeah.
Is this 3 over 10?
Well, right now, I'm just looking at the bounds, but I know the order may not be correct, but I do know this is true, right? Integral from -1 to 3 and from 3 to 10 will give me that region. Okay, so now we have the definite integral from -1 to 3, which we can just go ahead and make a clean substitution. But these two are related, but not quite the same. So what adjustment could we make?
Flip the values.
Yeah, because we know that if 10 to 3 is 9, then we know integral from 3 to 10 must be equal to -9. Okay, so now we can make a clean substitution, right? So now the definite integral from -1 to 10 is just 5 plus a -9, -4. Okay, so moving on to even and odd rules. So even functions are ones where the graph can be mirror image across the y-axis. So let's say I had a region, an even function between -a and a. So that could look like this. Let's say -a was here and a was here. So if it was truly an even function, then whatever we have on one side, we'll have a mirror image on the other side. So we know that the region from -a to a would be the same as if I were to just take one side of it and then double it. Okay. So this will be the same thing as taking just the integral from 0 to a and then just doubling it, because we know that the other side will be the exact same region. Okay, so basically, even functions, you're going to create a mirror image on both sides of the y-axis. Now, an odd function is going to be opposite but equal on both sides of the y-axis. So that means if I have a region that is, let's say, a +6, then the other side will be a what? A -6. So that means if I were to total up the regions on both sides of the y-axis, as long as I'm the same distance from both sides of the y-axis, it's always going to total to be 0, because anything I have on one side is going to end up matching that value, but the opposite sign on the other side. Okay, so we're going to use these properties to practice through these examples below. Suppose we have an even function, and we have a region from 0 to 3, and then a region from -4 to -3. It says find the region from -4 to 3. So my suggestion for these problems is start with your shorter interval first. I know that there's some of these problems, it may not matter, but I think that's always a good rule of thumb, especially when things start overlapping. So start with your smaller interval first, and then build your graph. So from -4 to -3, I'm going to create a region that is called 4. So I'm going to make it above the x-axis. Okay, just some arbitrary graph here, just so I can have something to work off of. Now, as soon as you have this, go ahead and fill out the other side, because if it's an even function, what do you know to be true on the other side? Also a 4, right? There's a reflection on the other side. Okay, so right now it does feel like, okay, you're going to ask, well, wait, why did I do it this way? I could have just done it the order. So this is for kind of this would be a good method for future problems. Okay, just if we can follow the step, and then we can adapt to any other issues that we're going to see later. Okay, so start with a shorter interval, build the other side, and now let's look at the larger interval. The larger interval is from 0 to 3. 0 to 3 is giving me 2. So the other side is going to be what? 2 as well. So start with the short interval. Then,
Add all those up.
yes, right. I'm writing out the steps for future problems too. Fill out the other side. And then work with the larger interval. Okay, not the larger area. We're not doing smaller area, larger area in that order. You look at the interval, don't look at the size. Okay, so now we are going to add up whatever they want us to add up. We want to add up the region from -4 to 3. So that's going to equal what? Well, 12 for the whole region, but just from -4 to 3 will be what? 8, yeah. Okay, next one, same as example 3, but now we want to make it an odd function. Okay, so we're trying to find the integral from -4 to 3, but we're going to ignore that. Which one do I want you to start with? Smaller interval, right? Not the smaller area, smaller interval. So okay, once you have that smaller interval built, go ahead and fill out the other side before you move on to your larger interval. What can I fill out on the other side? Now it's an odd function here. -4. Okay, let's fill out this one here. The integral from 0 to 3 is 2. Which means that the other side must be what? Okay, if we were to add all this up, it would be 0. But it's not asking for the full interval, right? It's only asking for -4 to 3. That adds up to be 4. Okay, so example 5 is where we're really going to see the benefit of it working from this in this order. Okay, we're back to even functions. We have the region from 3 to 6. We have the region from -6 to 3. We want to find the integral from 0 to 6. Where do we start?
-6, 3, first one.
Yeah, this was a smaller interval, right? Smaller interval because this spans a larger distance x value wise. Okay, so we'll start here. Okay, before we do the larger interval, what can we do? Let's create a mirror image on the other side because it's an even function. Now, we'll move on to the larger interval. The larger interval is going from -6 to 3 is 12. Now, we don't want to do this. We don't want to overlap this and call it 12. We already have 7. We just want the remaining regions to add up to be 12. But if this is 7, then the remaining must be what? Must be 5. But it's an even function, so what has to happen? It's going to split evenly between on 5, right? So 2.5, 2.5. So let's double check this is true here. The integral from -6 to 3 is 7 plus 2.5 plus 2.5. which is 12. But we don't want to do this. We don't want to do a full overlap because this is already set in stone. We don't want to build on top of this. We just want to fill out the remaining portions that will add up to that number. Now, it's asking for the integral from 0 to 6, so what's that equal to? 9.5. If you don't do it in this order, then it makes it harder because if you do the larger interval and it just feels harder to know. Yeah, I think it's nice to start off with these two steps because then you kind of have that foundation set and then you're not thrown off by the larger interval, especially if there's an overlap because you already have something to establish to start with and you can fill out the remaining regions with the information for the larger interval. Okay, next page. Okay. I want to introduce to us a couple of new integral rules and also talk about, and we're going to try to fill out the rest of our integral rules over the course of today and Monday. Now, we have the first rule that we learned for antiderivatives is power rule. So it says, what would happen if we attempted power rule for this problem? Okay, so we have 1 over x dx. We do know that if we want to make it into a power rule problem, we got to move that x up to the top. What's going to happen if I attempted power rule? I end up with x to the 0 over 0. That doesn't work, right? So this is the one exception where power rule doesn't work, right? Any other power, -1/2, -2, 1, 2, right? Even 0 we can handle, but a -1 power rule is going to break down, right? You cannot divide by 0. Okay, so this is the one exception the rule that we have to counter this exception is this natural log integral rule. So whenever we see an integral of 1 over x dx, just know that it's going to be a natural log absolute value of x plus c. By absolute value. We want to ensure that everything inside this region is going to, well, first off, we want to make sure that any x value is represented as just positive because natural log cannot take a negative value. So to ensure that, we have to protect it with an absolute value. Now, if you recall, we do have a derivative rule that says natural log of u is u prime over u. So if we undo this process, ignoring that u prime, the integral of 1 over u is just natural log of u. So I know this is a workaround for power rule, but this is also a reverse of derivative for integral, for logs, for natural logs. So this is a important one here. I would say with integral rules, there's the big three. There's power rule, there's natural log, and there's also exponential e to the x. Those are the ones that are going to be guaranteed to show up on the AP exam, and then the lesser ones may or may not. Okay, so let's look at example 1 here. Example 1. First, we always want to explore, is there a possibility for me to rely on power rule or expansion? What's our answer to that? Because Yeah, more than one term, right? If it was 2x over x squared, then that's fine. We can move that x up and then we can go from there. But as soon as there's more than one term, we're stuck. Okay. So understand that we're stuck with power rule. I mean, we're stuck not being able to use power rule. And second, there is no such thing as quotient rule for integrals. Okay, so we can't adapt a quotient rule. So if we can't do power rule and expand, our next option is use substitution. So what could be, I know we don't see parentheses, but if you had to guess, what could be a u value that we can use? X squared plus 1. Remember that you want your u value to be a fairly significant portion of your problem. Because if you only pick and choose portions of it, you're going to be left with something where it's not going to quite fit into a rule, right? Because we have such restrictive rules, we want to make our u value as significant as possible so that we can create an easier problem that will match the rule that we have in front of us. So a lot of times it's going to be, if there's a numerator and denominator, it's usually just the numerator, just denominator. Now we're going to come across a exception to that rule real quick, but for now, the denominator makes sense. Okay. Du dx, what's the derivative? Solve for dx. Make our substitutions. Remember, I like to underline my priorities, right? I don't care about the 2x right now. I just want the replacement for u and the replacement for dx. What happens here?
2x.
Yeah. The 2's canceling out, that's, you know, if it didn't cancel out, it's no issue. It's the x that we were concerned about, right? If the x's don't cancel out, we have a problem. But here, this is fine. Our x's go away. That's a good sign. And second, we look and there's a rule that matches exactly with what we see in front of us. If there's a coefficient, we can cover up the coefficient. If we cover up the coefficient, our integral that we have in front of us should match exactly with the known rule. If it doesn't match exactly, then we don't have a rule to use. Okay, it is very restrictive. Integral rules is restrictive. We cannot play and adjust and add to it. So, but this does match the rule perfectly with one that's available to us. So we can jump into our integral rule. Natural log absolute value of u plus c. Remember, u is only a temporary variable. We have to bring our answer back in terms of what? X. Okay. Example 2. Can I expand my way through this? No, I can't merge natural log and x together and get it to be something that I can use power rule with, right? So this one, we have to kind of consider, well, we have a couple of options here. We can't do expansion. There is no rule that looks just like this one. We got to go through use substitution. So we got to kind of play around and think about what is a u value with a derivative that will match and pair up nicely with what we want to do. So we have 3 options. Either our u value is x, it could be natural log of x, or it could be the whole denominator, x natural log of x. Natural log of x. And the nice thing about natural log of x is that the derivative of natural log of x is 1 over x, right? U prime over u. And that will pair up nicely with this, right? If we let our u value be x, we're left with 1 over u natural log of u, and we don't have a rule for that. If we let the u value be the entire denominator, then we got to go through product rule, and product rule will produce something that has no pairing in the problem. So yeah, just understand that, these are the more difficult U substitution problems when you don't know exactly what the U value is, and you almost have to kind of look ahead and play through your mind, what's the derivative of my potential U value, and can I see things fitting into this puzzle that I'm working? Okay, so my U value is natural log of X. Du over dx is U prime over U, which is 1 over X. Cross multiply, so dx equals X du. So I have my substitution terms. I'm just going to replace natural log of X and dx, leave the X alone. Okay. Do the X's cancel out? Yes, so we know that we're on the right track, right? If your X's don't cancel out, that's a red flag. You got to go back and reconsider. Maybe I didn't quite do something right. Okay, 1 over U du, we have a rule for that. Natural log as the value of U. Remember, again, U is your temporary variable. We got to bring what back? Yeah, so it's going to feel a little strange here. This is natural log of absolute value natural log of X plus C. Okay, let's look at example 1. We'll skip 2, but just look at example 1 here. It says complete the square and long division are 2 skills that helps us manipulate the integrand until it becomes something that we can work with. Okay, so I'm not going to do long division here. I'm going to do synthetic division. It's quicker. It's more efficient. It's a little bit more gimmicky than long division, but I just haven't seen on AP exams where long division is needed. I've only seen synthetic division, so I'm just going to stick with that. All right. So, but right now, let's just ignore that this process, and let's just look at the problem in general. Okay. Whenever we see a problem in front of us, we always want to consider what? First, power rule expansion. Can I do that here? Because 2 terms, right? If it was divided by X, then that's fine, right? That can separate, divide into individual fractions. I can clean that up and no problem. But as soon as I have that X minus 2 there, I'm kind of stuck, right? Okay, so we know that our first option is out. Our second option is U substitution. But what's the issue with U substitution here? Right, either if I let my U value be X minus 2, my derivative has no chance of canceling these out. And there's just too many variables. I can't do this change of variable thing with all these variables here. And if I let my numerator be the U value, the derivative is not going to match this either, right? So we don't see a nice pairing. Okay. Yeah.
Should we only use the
Substitution.
When there's one term in the numerator?
Typically, the rule of thumb is you want to use U substitution if your degree in the denominator is higher than the degree in the numerator. That's typically is going to be a better fit. There's always exceptions, but here, if your degree is higher than numerator than denominator, then we know that, especially if it's a linear term down here, this is kind of like the look for the synthetic division that we're going to do. Okay, now we're going to use synthetic division process not to find the answer. We're using long synthetic division to create a version of the problem where we can actually find a rule to use. Okay, so the idea is that we are going to split this up into easier parts, but we can't use power rule, at least not at this stage. Okay, so my degree is higher in my numerator. I have a degree 1 in the denominator. I can't use U substitution, so my next option is synthetic division. Okay, so synthetic division, what I want you to do is I want you to pull the factor out. So if you set x minus 2 equal to 0, you'll get x equals 2. So you're going to put 2 outside a half box that you're going to create. And I'm just going to place the coefficients of each term. And if there is a degree that is skipped over, I need a placeholder for that degree. So I just have to start off with the highest degree. My highest degree is x cubed. Don't put the x cubed there, just put the coefficient. So 3 followed by, -1, -5, and 1. Are there any degrees that was skipped over? No, so that's fine. Okay, so all these numbers are good. Okay, what you're going to do is you're going to bring the first number down below the line. Next up, you're going to multiply. 2 times 3 is, put that number on in the second column. And then you're going to add 5. Repeat the process. 2 times 5 is 10. Add 5. 2 times 5 is 10. Add, which is 11. Now, we're dividing by x to the first power. So what's going to happen is your degree, your cubic, is going to fall to a degree what? 1 degree lower, right? If I'm dividing all these by x to the first power, everything will fall by 1. So this is now going to be 3 what? X squared. And then from here, you're just going to do a degree lower for each term that follows. So 3x squared plus 5x plus, and then guess what this is called? The remainder. So remainder tells us I cannot divide any further. It's not a perfect fit. So if I can't divide any further, I'm going to show this is the portion that does not divide out. It's the 11 over x minus 2. But everything else divides out. Now, this is not my answer. This is only a simpler problem for us to approach the integral with. Okay, so now I want you to put an integral notation around that expression, and we're gonna have a much easier time because the first 3 terms I can just use what? Power rule. And the last term is just going to be a baby u substitution problem. Okay, 3x squared becomes x cubed. Yep. Okay, we're not going to do example 2, so I'm going to use that space if I run out. Plus 2x squared. Plus 5x. Okay, so now I'm going to step to the side here and just handle this small u substitution problem. So if you see this problem in front of you here, obviously we can't split up. There's too many terms in the denominator. We have to go through u substitution. What could be our u value? One over u du, the 11 comes out as a coefficient. The integral of 1 over u is 11 natural log of u, and then natural log of u. U gets replaced with absolute value of x minus 2. Now, some of you guys are going to be able to get comfortable enough where whenever you see this baby u substitution problem, some of us will just be able to jump directly from here to here, which is fine. Okay, so if you see this and you understand, okay, there's not going to be anything that's going to come out of my derivative. It's just a natural log of this plus c. You can do that. Okay, but if you feel like you just want extra confirmation, this is fine as well. But we're going to see enough of this, I think, where you're going to be able to just jump from here to here and not have to go through the full u substitution steps if you don't want to. Yeah.
Oh, if you like skip over a degree, you said you needed a placeholder.
Placeholder, right. So let's say it was Okay, let's say it was this problem here. Then you'll do the factor, so it'll be one outside your half box. Okay, we start off with what? Oh, sorry, thanks. Integral of 3x cubed plus 2x plus 1 over x minus 1. Our factor is 1. We're still going to start off with 3 because 3 represents the highest coefficient of my highest degree. Okay. What's my next degree? X squared, but I don't see an x squared there, so I need to put a what for x squared? 0. And then the 2 will be for x, and then the 1 will be for. Now, if there was no coefficient, sorry, if there was no linear term, you don't have to put a 0 placeholder if it's at the end and if it's not used. Only if something is skipped over, then you got to make sure you have a placeholder for it. But if it didn't go all the way down to a constant, you can stop at the 2 and it'll be fine. Okay. These are the last set of kind of messy rules that we have to be responsible for. Now, if you think about trig rules or inverse trig rules, we had these 3, right? These are the important ones because we know that these led directly to the ones involving arc cosine, arc cotangent, arc cosecant. So if arc sine's derivative is u prime over square root of 1 minus u squared, then the antiderivative of this will bring me back to arc sine. So with some slight adjustments. So if I have du over a squared, square root of a squared minus u squared, that ends up being arc sine of u over a. Du over a squared plus u squared, I got to do 1 over a, arc tangent of u over a plus c. And the arc secant is this mess, but it kind of resembles the derivative for arc secant. Okay. Now a is the constant. So if you're looking in the denominator and you're reading the problem, trying to figure out what is a, what's u, your a is going to be the constant and your u is going to be the variable. So our goal is we want to get it into this form. And once it's in this form, we can just fill out the right side. Okay. So let's look at example 1 here. This example 1 looks most like example 3, arc secant. So everything lines up pretty well. But if we know we're going to use an arc trig rule, we're always going to start off this way. Go ahead and create parentheses squared inside your radical. Now, what we want to do is we want to fill in these spaces so that the resulting expression is the same as what we started with. What can I put inside the first space? X. Because x squared is the same thing as x squared, right? No changes there. Okay, I want to adapt to 9 so that it can be something to the second power, 3. So if you go through this exercise, then you're going to be able to see your a and u value without any trouble. Sorry, your u value and your a value without any trouble. Right? Go through this process and you're not going to accidentally put down a 9 for your a value. Okay, so now we have everything that we need. Our u value is x. Our a value is 3. If I want to find my derivative, du over dx is just 1, so dx equals du. So my initial goal is, can I make this look exactly like the rule that I want to use? Okay. So I'm going to pull the 5 out in front. If there's any coefficient, I can pull that out in front. Dx becomes du. I have u square root of u squared minus a squared. Okay, perfect fit, right? If I can cover up my coefficients, everything else should match exactly with the rule. Otherwise, I don't have a rule to use. Okay, integral rules are very restrictive. So perfect match. So now we can just spell out whatever the problem is asking for. So I'm going to start off with the coefficient. That's going to be part of my answer, times 1 over a. What's my a value? Arcsecant, absolute value of u, which is over 3 plus c. I can make that 5/3 if I want. Okay, example 2. What does this match up best with? Our tangent. Okay. So first thing is let's get that denominator to show parentheses squared. Okay. What can I adapt the 4 into? 2. Yeah, still x minus 1, right? So no adjustment needed there. Okay. All right, so our a value is 2. Our u value is x minus 1. We always want to find du dx. Make sure that we don't have any leftovers to keep track of. Force your problem to look exactly like the rule that you want to use before you use it. Perfect match. No coefficient to keep track of. So now I can jump into my rule. 1 over a. What's my a value? Arctangent of over 2. Let's see. Now I'm kind of guiding you through these problems, so it makes sense matching the rules. But looking at a problem like this, sometimes you may be feeling like, wait, how do I know it's not a u substitution? How do I know my u value is not x squared minus 9? How do I know that this is an arc-trig problem? An easy way to tell is look at the degree of your denominator with your degree in the numerator. If there is a gap of 2 or more, then that's an indication, with the denominator being the higher degree. Then with that gap, you know that it's not just going to be a u substitution problem. I got to involve arc-trig. So here I see a degree 2. I know it's under the square root, but we're focusing on what we see in front of us. Degree 2, and numerator is degree what?
0.
Degree 0. There's a gap, right? When there's a gap with the denominator being higher, that's it. That's a hint that it's going to be an arc-trig relationship. Here we see degree 2, and top is degree 0. Again, there's going to be that arc-trig relationship. Okay, now let's look at example 3 here. This is hope I can squeeze this in. All right, number 3. We always want to go through our steps, right? Our options. Can I rely on power rule expansion with this problem? No, right? Too many terms in the denominator, right? My degree is not favorable for u substitution because if I let my u value be my denominator, it's not going to have anything up in the top. This is not going to be a long division, synthetic division problem because my degree needs to be higher up top than my denominator, which is not. So let's look at our last option here. Denominator is degree 2, numerator is degree 0. There's a gap, right? There's a gap of 2 or more. With the denominator being higher, we're going to have to involve arc-trig. Now, there's no square root, so we kind of feel like this could be a fit for what? Arctangent. But the issue is that we don't have a nice grouping of a squared and u squared. Right? It's not like the previous problem where we see a nice separation of a variable squared and a constant squared. So we have to go through this process called completing the square to produce this binomial squared variable with coefficient, right? Because right now I'm not able to get it into the parentheses. So we have to kind of adjust the denominator a little bit. So this is what we're going to do. We're going to take that x squared plus 6x plus 10, and we're going to play with it and create a different version of it so that it can actually fit into the rule that we want to use. So what you're going to do is you're going to create a space on between B and C and then to the right of C. So we're going to basically group the variables together. But I want to find a constant that will allow me to factor nicely. But whatever number I find, I don't want to change my overall expression. So if I do a +6, then I want to make sure I immediately have a subtract 6 here because I want to maintain balance. I don't want to change the overall value of my expression. So what's going to fill in here that will allow this to factor nicely is this formula, b over 2 squared. And that's going to go in both spaces. Okay, what's my b value?
6.
Okay, 6 over 2 is 3 squared is 9. This will allow us to factor very cleanly. Okay. Multiplies to be 9, adds up to be 6. 3 and 3, right? So I can merge this together to be x plus 3 squared. Plus 1, good. And minus 9 is 1. So now we have something that looks like example 4, feels more like something that we can use our tangent with. So we're not going to do example 4, so we're going to use that space. Okay, let's create parentheses in the denominator to further make this look like we're the form that we want. It's pretty much there already, right? X plus 3 and 1. Okay, what's my a and u value?
A is 1, U is x plus 3.
Okay. Find the derivative, get everything in terms of a and u. Make our problem look just like what we want to use. Perfect match, no coefficient to keep track of. We now apply our rule. 1 over a. So 1 over 1. Our tangent of u over a.
X plus 3.
Plus c. I can drop the 1. I can drop the 1 in top and bottom, so I can clean up to just be this. Okay, guys, you picked up the test review. I just want to kind of quickly kind of go over what to expect for this non-calculator portion. So problems that are just power rule, problems that we have used substitution for, power rule, use substitution, change a variable, evaluating bounds, second derivative, second theorem of calculus. I haven't shown you how to do the absolute value, but these are easy. We can sketch the graph and just adding triangles. Particle motion, but really it's just acceleration to velocity to position. Average value theorem. And I didn't get a chance to create a full version of the review. So I'm also including problems that we've learned recently, natural log rule, use substitution. I do need to go over exponential rule, e to the u, but that's just going to be, and then some of these I may not include. So I do want to spend Monday going over what rules that we don't have to worry about, at least not for this test, not for this test. But you can start looking at the back of the rules that we've learned. Okay, and I'm going to highlight the ones that we don't have to worry, or ones we can just focus on and not worry about. Okay, so if you have a chance, start looking over the test review. I know we're still playing catch up right now. I have the test scheduled to be Wednesday, so we'll have Monday and Tuesday to do our test review. Okay, go get your phones. Okay, great. 6.4. Okay. Just look there's 6.4. Those are good. Yeah, there are a couple of this. Okay, all right.
Send it out. You didn't see us. Because it's not like it's a lot. First, when you invite these, something.
If you're ever stuck on a problem, make sure you're simplifying.
Yeah. Work off.
Yeah.
So.
I'm
Yeah, don't have to have anything lines, just copy it. It shows me that you at least know this.
All my focus was heavy.
That was nice, it's really not good.
I didn't know, I never picked it up. See this, like.